welcome to this session. This is about bringing complex event processing to Spark streaming. Hope you'll have a good session. And stop me anytime if you have any questions. Before I begin, a couple of words about myself and my colleague here, Hoyoung Park. I'm Prabhu Tukaram. I lead engineering for the Stream Analytics product and the Event Hub product at Oracle. And Hoyoung Park is our architect and the primary contributor for integrating our Stream Analytics product with Spark. So just a quick question. How many of you work with Spark streaming? It's quite a few. Okay, good. Okay. So how many of you have heard of continuous query processors? Okay, that's a good sign. So we have a lot to talk then. So complex event processing, I'm sure you all know this by now. It is really about identifying business opportunities and threats in real time and taking automated actions on those situations. Traditionally, complex event processing is implemented with continuous query processors with READ engines. READ engines are essentially a rules engine, like can just ingest a network of rules and run those rules based on the situation. Again, complex event processing, the use cases for complex event processing are many. Sure, you already heard, like you used complex event processing for fraud detection, asset tracking and maintenance, asset management, predictive maintenance, churn prediction, whether it's a bank, whether it's telecom, you want to predict churn of a customer. You could also use complex event processing for log analytics and security incident event management. Okay, I have a short demo for you in 20 minutes from now, just showing you how Stream Analytics with Spark streaming could be used for identifying security incidents. Okay. So this is the agenda I have. I'm going to have a short introduction to continuous query processors, and then we're going to tell you what we have done to integrate continuous query processors into Spark streaming, and then a short demo, and then last 5 minutes for questions. So sometimes a continuous query processor is called an inverted database. It's called an inverted database because with traditional databases, your data is static, your queries are ad hoc. But with continuous query processors, it's just the opposite, where your queries are static, they're pre-registered and they're static, and your data is ad hoc, right? So your data comes in, and the queries are run on two instances. When a new event comes in, the query is run, or when there's a heartbeat. What we mean by heartbeat is, you can think of heartbeat as an empty event with a newer timestamp. Okay? And you need these heartbeats because if you want to, your window processing is all about progressing time. So if you want to progress time, you need heartbeats into the continuous query engine. Okay? So most continuous query processors offer a declarative language to define your queries. Queries could be a simple analytical query, or a query could be a pattern matching query. Now here's an example of Oracle's continuous query language. So essentially it's SQL-like. In this case, what it's doing is it's checking if the temperature from a sensor is wobbling over a 10-minute interval, and it's actually projecting the support levels, which is shown in the green there. Okay? So if you look at the query, all it's doing is looking for a pattern in data where it's looking for one or more A's followed by one or more B's C's, and D's, such that where A is defined as any event whose value is lower than the previous event's value, right? So continuous query process typically use declarative languages to define your queries. Okay? But the most important aspect is to detect a pattern like this, you have to do what we call event-by-event processing. And what does it mean to do event-by-event processing? Event-by-event processing means you treat every event as if it occurred at a discrete point in time. Okay? So, and patterns could span across batch boundaries, right? So essentially what we have to do is we have to take the micro batch from Spark streaming and convert it to an event-by-event processing, right? With micro-batching, you know that all events in the batch are pretty much identified by the same timestamp, which is the RDD time. There is no real progression of events. There's no real progression of time between events in the same batch. And again, there is also no progression of time when the RDD partitions are empty. As I mentioned before, if you want to advance your windows, you need progression of time. And for progression of time, you need heartbeats. And that is something we do automatically. Right, so when there's no data coming in, we can still propagate heartbeats across the queries. So the windows advance, and you get the alerts, right? And this is critical for missing event scenarios. Like, for example, you want an alert when an order received is not followed by an order shipped within a certain amount of time, and you want to maintain your SLAs. For scenarios like that, you need event-by-event processing, and you need heartbeat propagations. And doing that on a distributed system is challenging. And that's what we have done. We have solved some interesting problems on Spark streaming, but with a little bit of our own IP. Okay. So how does continuous query processing complement Spark streaming? Right. So it's a mutual relationship here. So CQP, or continuous query process, they are event-by-event, and the stateful processing. The engine maintains the state, regardless of what application you're writing. Right? The application doesn't have to worry about the state. When the application crashes and it's recovered, it restores the state and starts processing from that state. And of course, there is a lot of flexibility when it comes to windows. Right? You could do both a time-based window or a row-based window. As an example, you could say, give me the average of a stock quote in the last 10 minutes. Or you can just say, give me the average of a stock quote for the last 10 quotes. Right. There's a whole bunch of flexibility in terms of how you define your windows with continuous query process. As I mentioned, there's also automatic progression of time. And you could detect patterns across boundaries, across events. It doesn't have to be at the start or end of a micro batch. It could span any, it could be fractional batches as well. Right? And of course, it also gives you a declarative SQL-like language for defining your applications. Of course, Spark complements continuous query processing. I have to step back a bit. So one of the reasons we had to rewrite our CEP engine on top of Spark streaming is because our CEP engine was essentially a single server, was designed for scale-up. What we mean by that is, if you had to handle higher volumes, you had to run our engine on a larger machine. And that is how it used to be. But with Hadoop and Spark and the other distributed computing frameworks, it didn't have to be that way. So what we did was we rewrote our continuous query processing engine on top of Spark streaming to make it a distributed complex event processing platform. Okay. I'm sure you know some of this, so I don't have to go through each one of these bullets there. In summary, or in a gist, Spark streaming plus continuous query process give you a distributed, scalable, and fault-tolerant CEP platforms. Okay. That's a very high-level architecture of our product. Just a second. So you can see the continuous query processing engine has a lot of components. Deep down, it has a query processor. It has finite state automata to detect patterns across events. It also has a read engine for conditional logic. And more importantly, it has a geosensing cartridge where you can do spatial analytics. If time allows, I'll show you a demo of that as well. And also, it embeds a distributed cache. So when you look up data from a database table, the second time around, the engine doesn't have to go back to the database. It's already cached. And if you could see here, it's pretty much is running within a Spark executor. Okay? And after every micro batch, the state of the engine is persisted to HDFS for fault tolerance without the application developer having to worry about it. Okay? So how does it work? So essentially, we run the continuous query processor as a long-running task in the executor. Right? So it pretty much, the continuous query processor is launched as part of the bootstrap process, and every executor runs a continuous query processor. It's pretty much one-to-one with the executor. And the lifecycle of the continuous query processor is the same as the lifecycle of the executor itself. Right? When the executor comes up, the continuous query processor comes up. When the executor dies, the continuous query processor dies. Okay? So a little more detail on how it's being done. So you could think of this Spark integration, it's a very high level again. So you could think of the Spark integration as where we have extended Spark streaming. Right? So we have extended Spark streaming with our own D streams and own RDDs, where the compute method's been overridden for all this processing. And if you're familiar with Spark, you know a Spark application, essentially there's two phases. One is the DAG creation phase, and the other one is the physical plan execution phase. So during the DAG creation phase, the Spark context is created, and as soon as the Spark context is created, we know exactly where the executors are, so we can spin the continuous query process on those executors. And we also set up a DAG of SQL D stream. And for each SQL D stream, we have a query context. And I'll talk about what we mean by query context and what is a graph. So you set up the query context for each SQL D stream, and then that's the DAG is set up. But at the physical plan execution time, essentially what happens is every micro batch is debatched. Every event within the micro batch is assigned a unique timestamp based on the RDD time. And then on the RDD compute, the whole batch is shipped off to the continuous query processor based on the data locality. And then the results are retrieved and then again propagated to the next node in the graph. Okay. Of course, if HA is enabled, this continuous query processing engine's state is automatically checkpointed. Okay, the most important thing is that as an application developer, you don't have to worry about managing application state. Same thing. So when an executor fails, Spark, of course, starts a new executor. And when a new executor started, we restart a continuous query processor on that executor. And then we re-register the query. We restore the engine state from the snapshot. And then we continue processing the stream. OK. I think we have enough time for a demo. Okay, any questions so far? Okay, you can see that's the Hadoop cluster, nothing running. Previous applications have been killed. That's a web designer for a stream analytics product. By the way, this is a live demo. So So the web designer could be tied to any Spark cluster. So right now we support a Yarn-based cluster, or we support a Spark standalone. We're also going to add Kubernetes to this cluster managers, list of cluster managers. So right now you could see the web designer is associated with a Yarn cluster. Okay. So once you have associated the web designer to a Yarn cluster, you could pretty much build pipelines for any data streams. So it would take like 30, 40 minutes to build a pipeline, reasonably complex pipeline. So what I have done is I've already built a pipeline. So I'm going to simply walk through that pipeline for you guys. Also, quick questions. Are you guys familiar with Nginx? Okay, so Nginx is essentially it's an HTTP load balancer. So the demo I'm going to show is it's assumed that the access logs from Nginx is being streamed, and we're able to process those data streams using stream analytics running on Spark Streaming. There's one pipeline, so I'm going to just open the pipeline. So while the pipeline opens, I'm going to go run a feed. This is going to simulate a data stream on a Kafka topic. And you could see the application is already running on Spark. So by the virtue of opening the pipeline, it simply redeploys the pipeline to the associated cluster, and then it runs that pipeline. So let's go take a look at this Nginx stream. So this is your raw data. So this is the very beginning of your stream. It's a raw stream. It's telling you exactly when did the HTTP request come in, what's the remote IP from which that request came in, who's the remote user, what endpoint is it going to, what is the response from the application server on the back end, and what was the agent that made the HTTP request. So this is a very raw stream, right? So but you could simply navigate through this pipeline to see exactly what's happening with the processing logic. So you could see here, for example, when I click the next node, it is essentially dropping anything that starts with a 200, because anything to do with 200 and above, 200 and between 300 is a successful request, a successful HTTP request, and you don't have to worry about that. So you simply drop such requests. And it's as easy, if you want to drop it, you can see what's happening here is I'll just apply a filter here that says the response allow only events whose response is greater than or equal to 200 through the rest of the pipeline. Right. You see now, I see a response code of anything other than 200, but I still don't know exactly what this means. So the next stage in the pipeline, if you see, the next stage in the pipeline is doing an enrichment of the data. What it's doing is it's doing a database lookup, and of course it's automatically caching it. And it's telling you, now it's giving you more details as to what these response codes mean, right? So you could see, for example, here in this case, anything to do with a 500 is really a server error, and anything to do with 400 is a client error, right? Of course, it depends on what logic you're trying to build. In this case, I'm just trying to look at different client errors and different server errors, try to aggregate some data. Like, for example, if you look at anything to do with 300 is essentially it's a redirect. Let's see, yeah, there are redirects. And here I'm just doing a stats here. I'm just trying to calculate exactly how many times there's been a redirect for a certain endpoint, right? I guess I have some visualizations too, so it will tell you exactly how many redirects are happening for each of those endpoints. Right. So that's that part of the processing, but you can look at other parts of processing as well. Like if you go here, for example, the client errors, this is anything to do with 4xx, right? So if you look at the next stage, it's saying it's looking for unauthorized access over a 10-second time window. I think it's a 10-second time window with a slide of 10 seconds. It essentially is a tumbling window. right? So you can click on it to see if you want to change that. But essentially, it's also looking for unauthorized access for a certain time window. It's also doing some interesting things like it's actually grouping all this data by the remote user and the remote endpoint. And then it's counting the number of such unauthorized access. Right. So, of course, the filter data, it looks like it's looking for a response code of 401 or a 403 and number of attempts greater than or equals 1. Okay, so if you find the number of attempts greater than or equals 1, then you can take some action on that data. So essentially, this is saying you could blacklist the user or you could notify an admin. Okay. So any questions so far? Okay, so once you build your pipeline, essentially you can publish the pipeline, right? So when you're publishing the pipeline, it's exactly the same as any other Spark application. So you could control exactly how many executors you want to run this application on, how much memory you want to allocate per executor, how many cores. It's exactly the same as a Spark application. The life cycle of this application is no different from a Spark application because it is a Spark application. Okay. But you can see that this application is a draft application, which means I may or may not decide to publish it. Once you publish it, it's going to run on the cluster, even after you log out. But if you don't publish it, and if you quit the editor, what's going to happen is it's going to remove that application from the cluster. It's going to free your cluster. So it's killed. Right? But if you decide to publish it, it'll continue to run. So let me quickly show you the other capabilities. So you could see the pipeline could be pretty much, it could be conditional, it could have conditional logic, it could have queries, it could have a scoring stage where you can actually bring in a predictive model. So you could see here, for example, we have predictive models. I don't have any predictive model here, but if you could bring in your own predictive model, you can use that predictive model as a stage in the pipeline to score an incoming event. For example, if you have a transaction coming in, you could check if the transaction is a fraudulent transaction if you have a model that can determine if it's fraud. Right. So let me quickly show you how we don't have enough time to build a pipeline, but let's see if I can actually go import another application. So this is another application which is actually monitoring sensor data from a transportation fleet and is trying to assess the behavior of the driver, like if it's any violations, is looking for violations essentially, right? Okay. Yeah. Okay, so if you go back now to your pipelines, you'll see there are two pipelines. There's another pipeline, which is the driver behavior pipeline. So let's take a look at that one. So before I take a look at that one, I need to start a feed for that. Okay, so this is real data from New South Wales. Historical data, of course, very old data. Okay, let's go open that pipeline to see what's going on there. You'll see that if you go back to your cluster, you'll see the application has been accepted. Refresh again. It says it's running. If you go back to your Stream Analytics product, okay, so let's go back and look at this raw stream again. So the raw stream, it's coming from a sensor device. It's telling you exactly the ID of the bus. It's telling you when the data was created, what is the position of the bus, the lat and long, the speed of the bus, who's the driver, and which highway is it plying on. All right. So if you look at the next stage, in the application, it's saying remove all the stationary buses. Essentially, it is, if you go look at the data, it says it's only looking for buses where speed is greater than 0, right? So, yeah, and then the next stage in the pipeline, if you look at this, what this is doing is it's doing what we call geoprocessing. So it's essentially filtering any bus which is not within those geofences, right? So we have a set of geofences which we have defined. So if you look on the right-hand side, that's the configuration of the stage. It is saying the geofence, or the set of geofences is Sydney, and the field from the stream is called lat, and the field from the long field from the field is called LON. And then, of course, all this data is automatically partitioned for you. If you see the object key there, it says partition all this data by bus ID. And what that means is an event for a specific bus will always go to the same engine, right, for processing. And if you look at the visualizations there, it's essentially telling you, it's essentially removing all the data which doesn't fall within those geofences. Okay? And then, of course, the next stage is just calculating the average speed over a 1 minute window using a slide of a nanosecond. Okay. If you look at summaries, it's just calculating the average speed. It just says, sorry, it's here. Okay, just looking for the average of the speed column. Same thing, it's next stage is checking for violations. This is what we call business rules. So you could define business rules on the stream, where here you have a complex condition. It's saying if the average speed is greater than 35 and average speed is lower than or equals 55, then set the violation category to minor, right? So these are just business rules. You could add as many rules as you want. So you just add business rules on top of this data, right? Yeah, and then the next stage is essentially getting the driver details for all the violations, and then sending those violations to an end system. It could be an insurance application, or it could be Department of Motor Vehicles. So whatever action needs to be taken, you could take that action on top of the data. Okay. So yeah, that's pretty much what I had to show. Essentially, we want to just talk about how we have integrated Stream Analytics into Spark Streaming, and it runs as a Spark application. Okay. So do you guys, any questions? Shifted, yeah. 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 So if you look at this, this is calculating the average speed. It's calculating the average speed of the bus using this time window here. It says the range is 1 minute, and the slide is, the evaluation frequency is nothing but the slide, saying take 1 minute of data, compute the average, but keep moving the window every nanosecond. But if you set the slide or the evaluation frequency to the same as the range, it means you have a tumbling window. Right. Yeah. So it's as simple as just setting the range. So yeah.
You mentioned that you use state machine and automaton for pattern recognition.
Yeah.
Can you just elaborate a bit, how do you partition or distribute those state machines?
So the partitioning is happening on the data, right? So so as I mentioned, like for example, in case of this demo, every bus is sending a reading, let's say, every second, right? There are 5,000, 10,000 buses. Every bus is sending a reading every second. So we have to make sure, because we're computing the average speed of the bus, so the reading from every bus has to go to the same engine, right? So the way that happens is, if you look at this here, the partitioning criteria, so if you look at this, if you look at summaries, it says group by ID. See? So what happens is when you say group by ID, we automatically know that we could partition this data for you. And we send, whenever data comes in, we send it to the right executor, which is running the continuous query processing engine.
And then, in the software point of view, well, in the stream application point of view, that means that you have one state machine within one operator?
It's one state machine for one pattern. Okay, in this case, it is not a state machine. It is just, you're just computing an average over a time window, right? So it's not a state machine. But let me step back and say the previous application. If you look at, let me show you the previous application. Let's go look at that one. So if you look at this one, so here, if you look at this branch here, it's looking for a sustained outage. What that means is, if you encounter any 5xx errors, it means it's an error on the server side, right? And with server, if those errors are not fixed, let's assume they're fixed. If they're fixed, you're going to get a 2xx back within a certain amount of time, right? So in this case, you're saying, is looking for a pattern called A is not followed by B, which means a 5xx is not followed by a 2xx within a time window. Duration is 2 seconds. For the demo, I just kept it 2 seconds. So it's looking for a certain pattern. Within 2 seconds, if a 5xx is not followed by a 2xx, for the partition criteria is a request, which means for that endpoint. So you could conclude that the endpoint is down, or there's a sustained outage, and then you could raise an alert to the IT. Right. So here, this is a pure pattern matching use case. And for this pattern matching use case, the finite automata would kick in. But as an application developer, don't have to worry about how these things happen, because it's a zero code environment. Right. Of course, we all know it cannot be completely zero code, so we also allow you to plug in your own Java code. If you look at the stage, there's something called a custom stage. So you could plug in your custom stage, and you could implement your own Java code for something that's not available out of the box. Yeah. Yeah.
How do you deal with schema on Kafka, for example, where you pull the data in? So how do you deal to find out the schema? Do you need to define that, or you have something like schema message stream?
Yeah. So if it's JSON messages that's coming in, JSON messages are self-describing. So when you create a new stream, so let me show you quickly. So let's go create a new stream. Let's say, yes, 54. So it says stream type is, we could pick as Kafka. It says pick a connection. There's only one connection, so I can pick Kafka 1 as my connection. So it automatically infers the topics. So it says those are the topics that's available. So I'm going to say pick a topic which is Nginx. And you say next. Don't have to worry about that. Say next. What it's doing is it's sampling a few set of messages from Kafka topic. And based on the sample, it's going to infer a shape for you. So it's already inferred the shape. If you don't like it, you can go fix it. You say you want to fix it manually. And then you could say, for example, this is time, so I'm going to just make this a timestamp, and so on, right? But if it's Avro, for example, if the data coming on Kafka is Avro, then you have to give us the schema, either in the form of JSON, or I think that's the only way. You provide a JSON schema. Okay. Yeah. Yeah, so any other questions? We guarantee. Nope. No, we guarantee. Yeah. As an application developer, the idea is that you shouldn't be worrying about all that stuff. Just build your application. Yeah, so we really, to be honest with you guys, we haven't benchmarked the product. But the continuous query processor, essentially, it's a predefined query. The query plan is already set up. It's kind of optimized. For example, if you're sharing the same time window on the same stream across two different queries, all that is optimized, right? So it's simply shared across the operator. The query plan is quite optimized, and the operators are shared across two different queries. In terms of memory, but so if you want to really know the performance of this product, so this is a product which is already there as a single server product. So we rebuilt it as a Java product. So if you search for Oracle complex event processing, there's like benchmark papers. You'll see that the latency is in microseconds and around 20,000 events per second per core. That's the benchmark the original product had, the continuous query processor had. So we haven't measured this in the context of Spark, but a couple of tests we did, we're close to 6,000 events per second per core. So there's no formal benchmark. But I'm sure there's room for optimizations. Hoyong, do you want to add something to that? No. Yeah, we knew the performance question will come up. Okay. I think. The Spark framework will be the bottleneck. It's, the processor is not a bottleneck. So the original product was designed for algorithmic trading, so with extreme low latency. Yeah. So the batch interval, sorry.
You said in the examples you had driver details like look up in the database table. If you like really scale horizontally, how does that work out if that's like, so in that example, it's just a database.
So how does that work out? So all this data is cached. So the hit is only once. So if you go create, for example, if you create a new reference, so let's say you want to create dbref. So you see, we could use, so right now you could use a database table as a reference, or you could use a coherence cache as a reference, but you could also use web service as a reference going forward. But let's pick the database table. And if you pick the database table, it says use a connection, let's say db1. You see this flag here, it says enable caching. So when you say enable caching, it actually tells me whether those entries expire, never expire, or when do they expire. So you could say in this case, for example, they never expire, which means you only take a hit once. For example, let's assume you want to enrich sensor data coming in. You're only getting the sensor ID, and you want to look up the manufacturer of the sensor, the location of the sensor, and so on. So when the sensor ID comes in, you'll take a hit once. So you go to the database table, look up all the details, but once the details come into the engine, it's cached then. In fact, it's a distributed cache. So I don't know if you guys heard of coherence. Coherence is a distributed cache. It's like cache or what's the other one? Memcache, yeah. So all this runs as part of the Spark application itself. So there's no need to set up an explicit cache cluster. You don't even have to know there is a cache cluster running behind. Yeah. Okay, I think we have a minute. Just take one more question. Okay, we're done. Thank you so much for listening.